Hi, my name is Tim Porter and I'm here to introduce this presentation on additive manufacturing, something we discuss a lot here at Home Solutions. Our team of design engineers are always looking for ways to improve products and find manufacturing advantages. We use 3D printing as a design tool, so application on the industrial scale is something we find very exciting. Now I'd like to introduce you to our presenter, Steve Wilson of Talbot Technologies. Talbot Technologies are at the forefront of additive manufacturing, and we're lucky enough to have Steve on our board of directors. Steve recently gave a presentation to an international forum on additive manufacturing, so we thought we'd invite Steve along to one of our weekly tech sessions and get him to present to the team. Then we thought we'd film it and share it with you. If you'd like to know more about additive manufacturing or Home Solutions, please feel free to get in touch. Contact details are provided at the end of the presentation. For now, we hope you enjoy watching Steve.
Okay, what we're going to talk about today is additive manufacturing, and you guys working as you do at the bleeding edge or the leading edge, you probably know a lot about additive manufacturing, but this is a perspective from just one company, from Talbot Technologies, and how we see the world of additive manufacturing. Firstly, the terminology is probably obvious, but additive manufacturing is the opposite of what we have traditionally done. So what we've traditionally done is subtractive manufacturing. We start with a block of steel, for instance, and we 3 or 5 axis machine it down to get a part. In additive manufacturing, we're going the other way, so we're starting from nothing and we're building a product up layer by layer. And what's interesting about that is that, and we'll talk about this briefly as we go through, that the two are starting to combine. So now there's quite a few instances of people developing equipment that is additive and subtractive. So within a 5-axis machining center, they might put a 3D printer. So 3D print the rough and then machine the final surface. So the things I'm going to talk about are our view of what the future of additive manufacturing is in the country and the world, and then how we use prototypes for sales activities, how we use them for evaluation and testing, how we have got into now using them for 3D printed molds, and that for a plastic manufacturer is probably as important as anything else, and into how we make printed tool inserts, and then jigs and fixtures, the use that we put additive manufacturing to for those, and then finally a world that I think is a big part of the future of additive manufacturing, and that's spares production. So what is the future? We've had some experts visiting New Zealand, and universally they've quoted this figure of about 4,000 units production a year. So if it's a relatively low cost product, the prediction is that by 2021, if you want more than 4,000 parts a year, less than 4,000 parts a year, it's likely to be made by either 3D printing or additive manufacture. And of course that break-even point changes dependent on how customized a part is and how high a value it is. So already 2 of the Formula One teams have selective laser melting machinery at the track, printing suspension parts to suit a specific track, and so at that level it's already worth doing. Another big part of the future is replacing wax and what we used to call the lost wax process, investment casting, where you print in this case some plastic parts, you form sand around them, and then you melt sand or plaster or whatever the moulding medium is, and then you melt the 3D printed inserts out. And specialist part manufacture, we'll talk about that, and I'll show you some examples of where we use it for that. Conformal cooled mould inserts is another big application, and what that means is typically if we make a mould for a part like this, we'll drill waterways going through and back, and so the water is somewhere adjacent to the part, but it's actually not that close to some parts of the part. With with additive manufacturing, you can make parts of the mould with cooling galleries that ape the surface, that they're always the same distance from the surface that they're cooling. And you can imagine that has major benefits in terms of the economics of making something. It's not only cheaper to make the mould, but you're actually making a part that will have better tolerances and you can make faster. It's going to always be a medium for prototyping. You know, we're always going to use additive manufacturing, I imagine, for prototyping, and plastic mould making will become more and more the norm for those of us that are in the plastics industry all the time. And then finally, an application that may not occur to you, but for 3D printed foodstuffs, already in Japan they're printing cakes, and printing and baking cakes to your own design. And I can imagine if you go to a conference in 5 years' time that you're more than likely, if it's a Homes conference, going to have lollies that are a Homes logo. You know, I mean, why wouldn't you if you can 3D print them? And so just to tease you out, there's a couple of universities around the world doing work on printing wax, and it's something that we've now got a program in New Zealand working on as well, because what happens in hives at the moment is you have a wood frame or a polystyrene frame, and the bees build their wax network, their honeycomb network on that. But that sometimes has limitations to how you clean up a hive, because you've got wood or you've got polystyrene. You can't necessarily steam clean. You've got a risk of splinters in the case of wood. It's not the ideal, but it's actually possible to print a wax honeycomb, and you save 60,000 bees a week's work doing that. So that means you're a week earlier in production. But the real benefit is that when you're finished, when a comb is fully populated, all you have to do is knife round the corner and steam clean a frame, and you're in business. Centrifuge the honey out. And of course in confectionery, that's an example of what they're doing in Japan, a lot of sort of 3D printed confectionery. So we have been using 3D printed prototypes now for about 15 plus years, probably about 18 years. And in the early days, those were SLAs. Nowadays, they've migrated to all the other types of techniques. So these are road cones, and we wanted to develop a new road cone for two applications, for the standard road cone and for a shorter one with a solar-powered flashing set of lights for road stops and things. And to get through NZTA requirements and testing, we built prototypes, because you don't want to build $150,000 mould or whatever it is just to test to see whether you've got it right. And so that allowed us to actually get them out in an environment, and it allowed us also to show a client, a potential client, what they might look like out in the field by clever trick photography. We've always done this for the electronics people that we supply. So typically, most of you are mechanical engineers, and you'll know that we very rarely make mistakes. But our compatriots are electrical engineers; they never get anything right. And so a printed circuit board always grows between the time it was designed and the time it gets installed in the housing. And so what additive manufacturing has allowed is for a prototype to be built, find out that the guys have expanded the printed circuit board, and then finally build the part to fit what they actually made. And that in the electronics industry has sped up the time to market dramatically. Just that change, just being able to try early and also do things like testing it, radio frequency interference shielding, and all those sorts of things with 3D printed parts. And often you find, actually it's got a name on it, so I won't tell you what we find, but often you find things that you have to send you back to the drawing board when you do make prototypes. That's a very early SLA. When they first started, SLA uses a laser to photosynthesize a liquid polymer and build it up in layers with the laser that's directed by mirrors. And in the early days, those photopolymers didn't print particularly clear. That's the sort of colour they used to be. Now, you think of an SLA, it's generally pretty white. So we make parts for the aviation industry. More and more, that's a target market for Talbot Technologies, and you've got very stringent, as you'd expect, standards around flying around planes, and it involves stringent fire retardancy testing and smoke testing and toxicity. It requires a crash test, often 16G deceleration crash test on all parts. And with the fact that you can often print a polymer that's very close to what you're going to use, it might even be the same chemical composition, but it's just a little weaker because it's got some facets in it or some porosity in it as part of the additive manufacturing process. You can often print a prototype as in that clear part and test it, and if it tests, you've built in a safety factor. So if it passes, you know the final part is going to, it can be pre-certified because it's going to be a stronger part than the part that was tested. And it allows, additive manufacturing certainly allows new concepts to be trialled. So this is a part that Holmes has had and will have more involvement in testing. And we weren't sure exactly what we wanted to do with it, or the client wasn't. It goes into ComFloor and it does seismic stiffening, but they also thought they might want to run cables through it and wanted cable trays, or they simply wanted a flat plate to shield off where the channels in the ComFloor are. With additive manufacturing, you can try all those things, and you can actually put them in place and see what they look like, and so a lot of the decision making around design is sped up dramatically. And particularly when you can actually test on 3D prototypes, and as I mentioned before, if the prototype material is chosen wisely, you can actually get approval to test a prototype and translate that to an approval in the final moulded part, because of the fact that you know what increment there is in strength from the prototype to the final part. So short run specialist parts is an area where I think 3D printing will not only become embedded in our existing service manufacturers like Talbot, but also will become embedded within any industry. Like we make, this is a end of a waterproof tube, LED tube lighting system for shade houses, glass houses, mushroom houses, and they all have different ways of wanting to mount the lighting, and so there's not the economics to make a mould for every potential clipping alternative. So the logical thing is that you custom print the brackets for a client's needs. So every time we sell a set of lighting for a glass house or a shade house or a mushroom house, we ask them what sort of brackets they want and print them. But that could be in their place. They could be printing them as well. I think some of what will happen is we'll see the boundaries blurring between what's a manufacturer's domain and what's the client's domain. And so that's what it looks like, the final LED tube. So this gives a photometric density about 5 or 6 times the fluorescent tube it replaces, with about 1/4 of the power consumption, and in a waterproof tube, and you can make brackets that just suit any particular application. So this is an example of a 3D printed mould. So when we talk about 3D printed moulds, we don't actually print a whole mould. We print inserts to go in a whole mould, as you can see there in the photos. So that means that the structural parts are always the same, and we have pockets that are a standard size, and we make printed inserts to go into those pockets. And they often have the cooling, and these are early ones that we did with a local client who you might guess from looking at the shape. And in the early days, we simply just put through bore cooling, but the way to print a 3D mold is to do conformal cooling. Like I mentioned before, the cooling galleries can be exactly the same distance away from the part at any one point. So these are examples, and these are high temperature nylon, as is that one, but we can print molds now in materials like PEI or PEEK even, that will stand materials that melt at 300 degrees or 320 degrees C. But this is really good for the general engineering materials. High temperature nylon does the job. So what that means, is a lot of the times now there's regulatory approvals to go through. So if you're in the survey market or the FPOS market, or the credit card transaction market, there's always some fairly high threshold testing to be done. So this allows the first 100 parts to be moulded by the same technique you're going to use and the same material as you're going to use for your production moulds, but you can produce them in 3 days or 2 days rather than waiting 8 weeks. And so that 8 weeks then is usable time for say the Visa MasterCard testing or the RFID shielding testing or any sort of testing you have to do before product release. So this is going back to what conformal cooling's about. So I think probably you'll know that one of the forms of additive manufacturing is selective laser melting, and in that you have a tub, reasonably large tub of powdered metal generally, and a laser is focused to selectively melt walls or build up a part inside that tub. And that allows you to produce really complex shapes out of materials like titanium, aluminium, nickel. There's an operation in Tauranga that's making customised silencers for guns for Canada and the States. And so you can have your own silencer which has your name on the outside, printed in titanium, and you can imagine how cool that is in the States. For one of your 100 guns could have a customised silencer. But it can also be done like this. This is a nozzle for an injection moulding machine, and you want to keep the plastic hot and molten through this piece, but you actually want to cool it round the tip so it forms a cold slug at the outlet of the tip, and it doesn't draw material when you open and shut the mould. And so that's an ideal application for conformal cooling. So this is, and these are all got cooling galleries that go up and back in each of these features on the part. And so that means you can get uniform surface temperature when a part comes out of a mould. So you've got uniform cooling, and you get a lot less residual stress because of that differential cooling that you often get in a moulded part. We used to make all of our jigs and fixtures by using an expensive 3 or 5 axis machining centre, but I see that slide needs a bit of work. Sorry about that, hadn't noticed that before. So these are jigs that now we tend to 3D print. So these jigs here are for spin welder. So in one of the ways you can weld plastics together is if the circular cross section is hold one still and spin the other at high speed with a weld allowance on the edge of it, and that friction melts that weld allowance, and eventually the viscosity and surface tension increases to the point that the welder spins. It can't turn it anymore, and you get a weld. And it's a very efficient way of welding parts, 95% plus of the parent strength. But the tooling can be quite expensive, but additive manufacturing makes it very cheap. You print a conformal tool very fast, a day, and you've got your tooling. And in cases like where you're doing jig boring, ultrasonic welding, ultrasonic inserting, there's nothing better than additive manufacturing for making jigs. And in the case of ultrasonic welding, where you're worried about attenuation of sound power waves, then you can rough out a substantial cradle of titanium or aluminium and just print the skin that goes in that's conformal to the part. Spears production is probably the area we're going to see advance so fast around the world, and it's already the case in automotive that additive manufacturing's widely used. There's some models of the BMW X5 that are differentiated by the grills under one of the differentiations is the grills under the bumper bar. They're printed, so each model has got its grill parts printed. Where there's left and right hand conversions, this one unfortunately they're both the same, but they should have been a left hand and a right hand. 3D printing has come into its own doing that, and in New Zealand we use it for trucks. So there are trucks manufacturers, 2 of them in New Zealand, that bring in trucks as well from the States and do left hand, right hand conversions by 3D printing. And then they probably hydrographically print these wood grains or whatever they want onto them. But there's now techniques going on, in development that we can skin 3D printed parts as we make them. And so there we are. There's an overview of, say, additive manufacturing. It's something that we'll all be involved with if you're not already. By 5 years' time, I think that every person in New Zealand will have a better idea of what it means. They say that we'll all have desktop 3D printers in their homes by 10 years' time, that they'll be as common as 2D printers are now. And I have no idea what they're going to be doing, but I'm hoping it's muffins and scones and all that sort of stuff.